Hi everyone, I'm Jayshri and this is Pava. And today we'll be discussing on arsenic determination in naphtha using graphite furnace atomic absorption spectroscopy.
Hello everyone, I'm Pava. I'll talk on the introduction about petroleum industry and arsenic. The word petroleum means rock oil and is derived from the Latin words petra, which means rock, and oleum, which means oil. In other words, petroleum is a mixture of naturally occurring hydrocarbons that may exist in any state depending on the conditions of subjected pressure and temperature. Petroleum is produced from reservoirs in either liquid, which is crude oil, or gaseous form, which is natural gas, depending on the state of the hydrocarbon mixture. Clearly, the word petroleum can cover both naturally occurring unprocessed hydrocarbons and petroleum products that are made up of refined hydrocarbons. The petroleum industry, also known as the oil industry or the oil patch, includes the global processes of exploration, extraction, refining, transporting, and marketing of petroleum products. Controlling trace elements in petroleum-derived products is an important aspect of the crude oil refining process, as the presence of certain elements in such products is linked to a variety of issues. Their presence in products like gasoline, diesel, and naphtha has been linked to decreased performance and stability. Certain metallic and metalloid species found in these derivatives can accelerate oxidative processes, reducing their thermal stability. Furthermore, their presence of potentially harmful components must be assessed, as these elements are emitted into the environment as a result of the use of petroleum derivative fuels as a source of energy in oil-fired power plants and automobiles. In 1959, Powers and team suggested arsenic would be present in naphtha as alkyl arsines. Studies conducted by Puri and Argolic in 1989 revealed that trimethylated and monomethylated arsenic are the predominant arsenic species in petroleum products. Arsenic is a metalloid element that occurs in nature in both organic and inorganic compounds. Arsenic compounds are poisonous and can be categorized into one of three broad categories, all with different toxicities, which are organic arsenic compounds, inorganic arsenic compounds and solutions, and arsene gas. Of all these compounds, inorganic compounds are of relatively greater toxicological significance than the organic compounds. Therefore, arsenic determination is very critical for many distillation processes in petrochemical facilities, because even a little traceable quantity of arsenic can induce severe and permanent catalyst poisoning during naphtha cracking. Hence, precise quantification of naphtha samples is critical in the refining and petrochemical industries. Due to the toxicological qualities of its components, it is also important for the environment.
Next, let's look into the sample type, which is naphtha. So, what is naphtha? Naphtha comes from Greek and is derived from the Persia word napht, which means crude oil. In other terms, naphtha is also used to refer to a group of volatile flammable mixture of liquid hydrocarbon. Generally, naphtha is a lightweight petrochemical feedstock obtained from the fractional distillation of crude oil. During the fractional distillation, crude oil is heated to be vaporized and fed into the bottom of a distillation tower. The vapor then rises through the vertical column with a decrease in the temperature. As the temperature decreases, groups of hydrocarbon begins to condense at different levels known as fractions. Each fraction would contain hydrocarbon molecules with similar number of carbon atoms. Out of these fractions, one of it is called naphtha, and it contains complex mixture of C4 to C15 hydrocarbons with boiling point ranging from 35 to 210 degrees Celsius. In petroleum industry, naphtha plays an important role as the main feedstock for downstream products. This is because naphtha is the main raw material or intermediate in producing wide range of chemical compounds such as ethylene, propylene, benzene, toluene, and paraxylene. Whereas in chemical industry, naphtha is used as a solvent for cleaning as well as a diluting agent in bitumen extraction. Other applications of naphtha includes varnish, fuel, diluent for paints, as well as shoe polish additives. Some properties of naphtha that should be noted includes its extreme volatility and high flammability. Besides, it is also classified to be carcinogenic. Hence, we must be very cautious while handling naphtha as they can cause skin irritation, stomach upset, and other health issues when exposed to them. Furthermore, due to their volatile nature, inhalation and ingestion should be avoided while handling naphtha by using proper protective gear.
Let's talk about the sample preparation for arsenic determination. We have to start with the preparation of solutions and samples. Firstly, distilled and deionized water with a specific resistivity of 18 megaohm from a millicube water purification system was used for the preparation of standards, modifier solutions and microemulsions. All containers, glassware, were soaked in 1.4 mole per liter nitric acid for at least 24 hours and rinsed 3 times with water before use. Nitric acid was further purified by sub-boiling distillation in a quartz sub-boiling still. Standard solutions were prepared by serial dilution of the 1000 mg per liter arsenic stock solution with 0.014 mole per liter nitric acid. Then, the standards for the THFA determination were prepared in 10% volume-to-volume ethanol to facilitate sample introduction. The organic standards were prepared by adequate dilution in base mineral oil and then 3-component solution with propan 1-ol, water and nitric acid was prepared using xylene to stimulate the matrix. Then, a mixture of 1000 mg per liter of palladium ion and 300 mg per liter of magnesium ion with a 0.05% volume-to-volume Triton X100 was used as the modifier. Then, the arsenic samples were stabilized immediately after collection as detergentless microemulsion by mixing 3 ml of the sample with 5 ml of propan 1-ol and 600 microliter of 0.014 mole per liter nitric acid solution. Then, it is filled up to a final volume of 10 ml with propan 1-ol. Finally, the mixture was then vigorously shaken in order to mix the components and to obtain a transparent solution. After that, arsenic determination was conducted in the graphite furnace atomic absorption spectroscopy. Firstly, 2 aliquots of 30 microliter of stabilized sample solution were introduced into the graphite tube and each injection was followed by 10 microliter of modifier solution. After the first injection of the sample and modifier, the first 3 stages of THPA and 2 stages of THFA of the graphite furnace temperature program, as shown in the table, were executed to completely dry the injected sample. After the second sample injection, the complete furnace temperature program was executed. Polyethylene laths were used to cover the vials on the autosampler to prevent losses by volatilization.
One of the most suitable technique for the determination of trace element is graphite furnace atomic absorption spectroscopy. Graphite furnace is also known as electrothermal AAS due to the usage of electrothermal atomizer. The general working mechanism of a graphite furnace AAS starts with the injection of sample into a pyrolytic graphite tube, also known as the atomizer. Then the temperature of the tube is increased slightly to remove any sample solvent in a process called drying. Then the pyrolysis step is followed to remove any sample matrices. Next, sample undergoes atomization process to produce free gaseous ground state atoms. These atoms will then absorb either UV or visible light at a specific wavelength and make transition to higher electronic energy level. The amount of absorption is then measured to determine the concentration of target analyte in the samples using a calibration curve. Lastly, the tube will undergo a clean-out process to ensure there is no sample residue left in the tube. Some advantages of using graphite furnace AAS includes a low detection limit ranging from microgram per liter to nanogram per liter. Besides, it also has a high selectivity, requires very small volume or amount of sample for analysis, as well as its simplicity in instrument operation. Besides, for complex matrices like Naphtha, routine analysis prefers direct analysis that doesn't require significant sample preparation, and graphite furnace provides that opportunity. Typically, graphite furnace and ICP-MS are used to determine arsenic in naphtha samples. The table shows the comparison between these instruments, which includes operational costs and possible interferences. Commonly, the issue surrounding the usage of ICP-MS is that it is unable to handle complex matrices as well as graphite furnace. Sample like naphtha can result in coke formation on sampler and skimmer cone in the ICP-MS. Besides, it also alters the plasma properties, making it unstable over time. Therefore, due to low cost of acquisition and operation, as well as high tolerance to complex matrices, graphite furnace is chosen to be the most suitable instrument for arsenic determination in naphtha sample.
Following are the instrumental parameters used in this study. Firstly, the model of graphite furnace atomic absorption spectrometer used in this study was AAS-5EA atomic absorption spectrometer equipped with deuterium background correction and a transversely heated graphite tube atomizer. The line source used was arsenic hollow cathode lamp operated at a current of 6 mA. Then, the wavelength used was 193.7 nanometer and the spectral slit width was 1.2 nanometer. Besides that, pyrolytically coated graphite tubes with integrated pin platform used for the measurements with transversely heated platform atomizer THPA was with length at 19 mm and inner diameter of 6 mm. Moreover, experimental tubes manufactured at Schwein University of Technology was used for the measurements with transversely heated filter atomizer THFA with length of 19 mm and inner diameter of 2.5 mm. Then, MPE-5 furnace autosampler was used for sample introduction into both atomizers, THPA and THFA. Then, argon with a purity of 99.996% was used as purge gas with flow rate of 2 liter per minute. Finally, integrated absorbance was used for signal evaluation and quantification in this study.
Lastly, we will look into 3 interferences and the solutions to overcome them. So first, for complex mixtures like naphtha, discrete analyses are preferred to ensure minimal sample preparation steps. However, direct introduction of field samples have raised few problems due to their volatility, flammability, immiscibility with water. Besides, researchers also found that sample preparation using organic solvent changes the analyte concentration due to the solvent volatilization. Hence, microemulsion or 3-component system have been introduced. Once naphtha samples are collected, they are immediately stabilized as a microemulsion with propan-1-ol and nitric acid. It was found that using this microemulsion sample, it showed the same sensitivity and concentration of arsenic even after 48 hours, thus making this a promising approach in reducing the loss of analyte by volatilization. Next, we'll look into transversely heated filter atomizer (THFA) in comparison to conventional transversely heated graphite tube atomizer with integrated platform (THPA). THFA increases the sensitivity of determination by 2 to 3-fold due to their smaller volume of filter tube atomizer, which results in a higher atom cloud density. Besides, THFA's narrow filter tube restricts molecules' entrance and permits only atoms to pass through the absorption volume, consequently reducing the background interferences greatly. Additionally, transverse heating of atomizers are done to prevent excessive spreading of fuel samples during thermal pretreatment from the temperature gradient of graphite furnace AAS, as this spreading can affect the precision of the results. Lastly, we'll be looking into the chemical modifiers used. The chemical modifiers used here are palladium with magnesium nitrates for the stabilization of arsenic. Due to direct analysis of naphtha, high pyrolysis temperature is required to remove the matrix, and this resulted in significant loss of the target analyte. Hence, chemical modifiers were introduced to stabilize the volatile arsenic and form stable compounds with higher atomization temperature. These are the references for the determination of arsenic in naphtha using graphite furnace AAS. In summary, these journals concluded microemulsion of naphtha samples can be integrated as a technique in determination of trace volatile elements. Additionally, chemical modifiers should be used to stabilize the volatile target analyte. As a result, the concentration of target analyte have been found to be similar over a period of couple days, and therefore these modifications can be made for the routine analysis of arsenic in field samples. Thank you.